All right, hey everybody. In this video, we are going to take a look at what we call LHospitals Rule. And LHospitals Rule will be, you know what, I'm not saying that right. It's French. We need to say it French, l'hôpital. If we don't say l'hôpital, then we're not saying it right. So l'hôpital's rule, it gives us a tool by which we can evaluate different forms of limits. Now, big picture idea here, right? In this chapter, we're talking about applications of derivatives. So the reason we typically see this section in a chapter of this nature is we're going to use derivatives to evaluate limits. Now, I just want to remind you in a prior chapter, at a chapter where we talk about limits, something we might have seen might have been, let's say, x squared minus x plus 2 over, let's say, 2x cubed plus 5x minus 1. So in a prior section, we may have seen a limit similar to this and talked about that in order for us to actually evaluate this limit, what we would need to do is use some algebraic trickery, right? So in other words, like if I look solely at the numerator, I'm only going to look at the numerator. It has a polynomial that's quadratic, and as x goes to infinity, that quadratic goes to infinity. And when I look at the denominator is cubic. That cubic function is going to go to infinity. So in that prior section, we would discuss that when we had in form like this, an infinity over infinity, we'd use a little algebra trick, and we would divide everything by the highest degree in the denominator. Now, the highest degree in the denominator is the x cubed term here. So what we would do is we would take everything in the numerator and divide it by x cubed, and then we would do the same thing in the denominator. We'd get 2x cubed over x cubed, we'd get 5x over x cubed, and minus 1 over x. Now remember, something like this is algebraically legal, right? Because technically what I'm doing is I'm taking this fraction and I'm multiplying by, I have that big of a marker, multiplying by 1 over x cubed times 1 over x cubed, right? So algebraically, we're multiplying by the number 1. So this is legal. And what this did for us in that prior section is we could simplify each of these. So in the numerator, I would get 1 over x, and I'd get minus 1 over x squared, and then that last term doesn't really simplify. And then in the denominator, the x cubes would cancel, and I ended up with 2, and then 5 over x squared minus, and then again, that one doesn't simplify. So through a little bit of algebraic trickery, we were able to get forms which we understood. We knew the value of. We knew their behavior. Right? So in other words, what are you doing? Get out of my way. In other words, what we were looking at here was something like a constant over something going to infinity. So I'm looking conceptually here as like the limit of, let's say 1 over x as x goes to infinity. So this is very loose mathematical notation here. This is not rigorous at all whatsoever. But this is like something that's roughly constant. No, in this case, it is constant over something growing without bound. So again, if I isolate the numerator, that's a constant. Denominator, that goes to infinity here. So anything, a constant over infinity, goes to 0. And if we think of the graph of 1 over x that we have in this case, the graph of 1 over x looks something like this. So as we go out to infinity, we can see the graph going down to 0. So we had the conceptual idea in a prior section that when we have something constant over infinity, that goes to 0. So the reason that this algebraic trick works up here is here's 1 over infinity, here's 1 over infinity, here's 2 over infinity. All of those things are going to go to 0. The limit of 2 is just 2, and then 5 over infinity and 1 over infinity. So what we end up with through this algebraic trickery is we really have 0 up here in the numerator, and then we have 2 in the denominator, and that just is 0. The limit of 0 is 0, right? All right, so what we don't want to do in this video, in this section, is look at these types of problems because when I have polynomial expressions, we don't really need to use what we're going to discuss in this section, which is L'Hospitals Rule. L'Hospitals Rule. All right. We could do other trickery like this. In fact, let me scroll back up. I mean, if you think about, usually in an algebra class, you would have probably looked at an expression like this. You would talk about rational functions, and you would talk about horizontal asymptotes, right? Whenever we let x go to infinity, right, we're talking about a horizontal asymptote. So as x goes to infinity on my graph, I'm looking at possible horizontal asymptote here in behavior. Excuse me. So usually in an algebra class, what you discuss here is you compare degrees. So usually you have this rule where you would say, well, if the degree of the numerator is smaller than the degree of the denominator, we're going to get a horizontal asymptote of y equals 0, which is what we got in this case, right? Usually if we say like the degree of the numerator is bigger than the degree of the denominator, there's going to be no horizontal asymptote there, right? And now that we've discussed limits, right, we know the cubic grows faster than the quadratic, so this fraction's just going to go off to infinity. And then we usually had a rule that said, like, if the degrees are the same, let's say we had 2x cubed over 5x cubed, as x goes to infinity, these x cubes cancel algebraically and we get 2/5. So I'm talking a little fast here with some review. In an algebra course, we would look at a rational function and we would just compare numerator degree to denominator degree. In a prior chapter in a calculus course where we talk about limits, we wouldn't have that conversation, even though we could, right? But we use this algebra trickery that we talked about over here because we were trying to connect to this conceptual idea, that when the denominator grows without bound, that term goes to 0. Now, what we want to look at in this section really are examples where we don't have polynomials. I want to be able to look at fractions where I have an exponential, or where I have a logarithm, or where I have a tangent function or inverse tangent function. So we want to be able to, kind of expand our horizons here. And instead of looking just at polynomial, let's look at other classes of functions. All right, so, for example, let's say we were looking at the limit of, let's say, x squared minus 2x over, let's say, e to the 3x. And we want to look as x goes to infinity, right? So here's an example where that algebraic trick wouldn't work, and the algebra rules that we memorized wouldn't work either. So the conversation of L'Hospitals Rule kind of goes like this. Now I'm going to back away from this example for a moment to just have some conversation, some exploration, and then we'll come back and we'll tie into L'Hospitals Rule. So we'll come back and we'll revisit this same example in a second. So in our exploration, what I want to do is go something very simplistic. So let's say we look at x over x cubed, right, as x goes to infinity. Now what we're really trying to do here is figure out like which one wins the race, right? We're really looking at like the limit of x over the limit of x cubed. So which one gets to infinity faster? That's really what we're asking. Right? So if we look at the line, right, a linear function does not grow as fast as a cubic. Right? If we think of the graphs, right? Here's a linear function, y equals x, right? Here's the cubic function. We can see the cubic gets bigger much quicker. So in a race, as we go to infinity, right, which one gets there faster? Well, the cubic is going to get there much, much, much faster. In other words, if I come out here to like x equals a million, what's that? That's 10,000, 100,000, million. And if I get out here to x equals a million cubed is much larger than just a plain old million. So as x gets bigger and bigger and bigger, right, as x goes to infinity here, what's going to end up happening is the denominator gets way larger than the numerator. So what we kind of have here is something relatively small-ish, right? Something relatively smallish over something getting really large. So what we, in essence, have there, this is kind of like 1 over x, like we just discussed, right? So 1 over infinity, right, our constant, something constant, let's just say something constant over an infinity, that's going to go to 0. And we're thinking again what we talked about a couple minutes ago. So in this example, in the race to infinity, the numerator doesn't get to infinity as fast as the denominator, right? So the denominator gets to infinity much quicker. So in essence, what's in the numerator is pretty small compared to the infinity in the denominator. And we're going to get 0 out of that, right? Now obviously, if I just look algebraically at this for a moment, right? If I just look at this for a moment, that reduces to 1 over x squared, right? And that's, 1 over infinity, which is going to go to 0, right? But I just want to talk conceptually with you. I don't want to talk about algebraic manipulation yet, right? Let's just discuss the concept. So L'Hopital's rule basically says, like, which one wins the race to infinity? So we have a race to infinity, if you will, right? And which one wins, right? Does the numerator win? Does the denominator win? Right? So we can see in this example, the denominator wins the race compared to the numerator, and our fraction drives to 0. Right? Now, what if we flip that fraction upside down? What if we look at x cubed over x? So let's take a look at, x cubed over x. Now again, we're kind of looking, right, as like a race to infinity. Which one gets to infinity faster, the cubic or the linear, right? We already talked about that. So we know the cubic gets to infinity faster, and the denominator is pretty small compared to the numerator. So in other words, we have something that's like something relatively small, right? I'm just going to call it a constant, although of course it isn't a constant, but it's a relatively small number compared to the infinity we get in the numerator. So this grows much quicker, and infinity divided by a number is infinity. Now again, I'm being really, really loose mathematically here. I can't say infinity divided by a number. These are all limits. So I have something in the numerator growing without bound, and something in the denominator growing much slower. Right? So being lazy and loose, can't really say infinity, right? Divided by a number, right? But we're talking in terms of limit processes. Right? All right, now what if the exponents are the same? I mean, let's say x cubed over x cubed. Right, and then obviously in a situation like this, actually let me put numbers in front of here like we had before, right? And in algebraic manner, I can see the cubes are going to cancel. So I'm going to get, 2 over 5, and the limit of a constant is just the constant, 2 over 5, right? Now, if we just think about in terms of growth, right, like which one gets there faster, obviously they're going to get to infinity at about the same rate. The cubic and the cubic grow at roughly the same rate. So neither of them gets there before the other one. They grow at about the same rate. So that's why we get this, constant ratio. They're growing at about the same rate. All right, so let's put this in the language of L'Hopital's rule, right? So basically what L'Hopital's rule is saying is we're going to see which one grows to infinity faster. So in other words, we're looking at a ratio of two functions, f over g, let's say as x goes to infinity, and we're questioning which of these gets there faster. So what we're really looking at is the rate of growth of the numerator, right, and the rate of growth of the denominator. That's what we're comparing. Whichever one grows quicker and gets to infinity first wins the race, right? And again, if the numerator gets to infinity first, the whole fraction's infinity. If the denominator gets to infinity first, the whole fraction is 0. And if they go at about the same rate, it's a roughly constant ratio. But here's what L'Hopital's rule said. L'Hopital's rule said when we don't have simplistic equations like polynomial in the numerator, polynomial in the denominator, we want to take this approach. We just want to compare the growth of each form, right, the numerator and denominator within that ratio. Now let's revisit that example that we had. All right, so up a page in our notes, we had started this conversation with this example here. So let's come back and revisit that conversation, and let's use L'Hopital's rule here. All right, now look, something that I didn't mention that I do want to come back and mention, and I will write it down in a second. Let's just discuss verbally. The only time we're going to use this L'Hopital's rule is if I have an infinity over an infinity. So there's no need to use L'Hopital's rule if I don't have infinity over infinity, right? So let's say my original, ratio, I get 1 in the numerator and 3 in the denominator, right? My limit is 1/3. I don't need L'Hopital's rule here. I don't need to compare the race to infinity. So only time we're ever going to use L'Hopital's rule is when I have an infinity in the numerator and an infinity in the denominator. If we look at this particular example, we have a quadratic, and as x goes to infinity, that quadratic goes to infinity. And then in the denominator, we have an exponential function. I remember, like e to the x grows to infinity. So we get an infinity in the denominator as well. So we do have a race to infinity, right? Which one's going to get there first? So what we're going to do is we're going to use L'Hopital's rule. So I'm going to put an LH on top of the equal sign to just point out we are applying L'Hopital's rule here. Now, remember, L'Hopital's rule, right, says that we're going to look at the rate of the numerator divided by the rate of the denominator. This is not a quotient rule. I'm not going to take the expression that we have here, x squared minus x over e to the 3x. So I'm not going to do a quotient rule. Only going to differentiate the numerator, only going to differentiate the denominator. So when I differentiate the numerator, I get 2x minus 1. And when I differentiate the denominator, I get 3e to the 3x. And I got a chain rule here, right? Derivative of e to the 3x is e to the 3x times the derivative of the exponent. So I have this expression here now. Here is the growth rate of the numerator. Here is the rate of change of the denominator. I'm comparing how quick these get to infinity. Now if I look at this independently, right, the numerator is still a linear function and it's still going to go to infinity, and this exponential still grows exponentially and goes to infinity. So in this example, we actually are going to use L'Hopital's rule a second time. And again, the reason we need to use it a second time is we have this infinity over infinity form. Which one wins the race? So I'm going to come back to 2x minus 1 and take its derivative. I'm going to come back to the denominator, take its derivative, and I'm going to end up with 9e to the 3x. Excuse me. Again, derivative of e to the 3x is 3e to the 3x times this 3 gives me the 9. Now again, I'm being really loose mathematically, right? If I plug infinity in, if you will, in the numerator, I'm not going to infinity anymore, right? I just have 2 in the numerator. What's in the denominator still goes to infinity. So anytime I have something constant over something growing without bound, that limit goes to 0. So we find out in this scenario, x squared minus x divided by e to the 3x, right, this limit that we started with, goes to 0. So in the race to infinity, which one gets there faster? We find out the denominator gets there faster. All right, now let's stop and talk intuitively for a moment. If I come back to my original limit here, x squared minus x over e to the 3x, if I just think intuitively, which of these grows faster? Well, an exponential grows much faster than a quadratic. So of course, this exponential is going to win the race to infinity, and I'm going to get, something small over something really large is going to go to 0. So usually within a context of a Calc 1 course, when we see problems like this, we could take that approach that we just discussed. We could look intuitively and ask which one grows faster. Now sometimes that's obvious, sometimes it's not. But I'm sure that your calculus teacher, even if you can figure this out intuitively, is going to want you to show analytic work. He's going to want you to justify mathematically the intuition that you have. So we will we will use L'Hopital's rule to justify our intuition in these problems. Now, let me come back then and restate what we just said. And I'm going to rewrite L'Hopital's rule and say that how do I want to say this? Something like this, right? That the limit of f of x over g of x will equal the limit of f prime over g prime when we have what we call an indeterminate form. So when the limit of f over g equals 0 over 0 or infinity over infinity. Right? So we call these the indeterminate forms. Right? So if I have one of those forms, then I have to use L'Hopital's rule. If I don't have one of those forms, then I don't need to use L'Hopital's rule. In fact, I can't use L'Hopital's rule, right? So only will I use L'Hopital's rule when I have one of these forms. Now, what we've just been looking at was like the race to infinity. We've been looking at infinity over infinity. So where does the 0 over 0 come from? So I'm going to do a little exploration again and look at where we would see, like 0 over 0. So let's come back to something really simplistic. Let's look at like, x over x squared, and let's go to 0. So again, if I could plug 0 in, right, what I get here is 0 over 0, right? Plugging in 0 for x, I get 0. 0 squared is 0, and I get this indeterminate form. So, all right, you might say, well, 0 divided by 0 is 1. That's not necessarily true, because we just saw above, infinity divided by infinity is not necessarily constant either. So the question again is very similar, right? Which one wins the race to 0 in this case, right? So in other words, if one of these gets to 0 faster, it's going to dominate the values of that rational, right? That ratio. So, what does that mean? All right, so if we look at x over x squared and we just think of, algebraic simplification, right? X over x squared reduces to 1 over x. And if I think of the graph of 1 over x, that looks something like this. So as x goes to 0, as my domain goes to 0, what does 1 over x do? It shoots off to infinity. So in this case, the 0 in the denominator causes the fractions to get larger and larger and larger. And this expression goes to infinity. 1 over 1 is 1, 1 over a half is 2, 1 over 0.1 is 10, 1 over 0.01 is 100, right? So as the denominator gets smaller and smaller, we can see the values grow without bound, right? All right, so when I have a 0 over 0, I'm going to have, again, the same question of which one wins the race. Now, if I take this fraction that we started with of x over x squared, and let's look at, the reciprocal of that. Let's look at x squared over x, let's say, as x goes to 0, right? We have the same question, which one gets to 0 faster? Now, if we think, algebraically, I'm not even using L'Hopital's rule here. I'm just simplifying x squared over x. That becomes just x. So the numerator is going to get to 0 quicker than the denominator, and then I just get 0 out of that ratio. Right? Now again, this is technically 0 over 0 here, and in this example, 0 over 0 becomes 0. In this example, 0 over 0 became infinity. So whenever I have one of those two indeterminate forms, infinity over infinity, or 0 over 0, I'm going to use L'Hopital's rule. The question is, which one gets there faster? Which one gets to infinity faster? Which one gets to 0 faster? So we're going to look at their rates of change, their derivative. All right, so let's take a look at a couple more examples. I'm going to do a couple for you, and then I want you to do a couple for me. So let's say we have the limit as x goes to infinity of ln of x over root x. Right? So again, I want to start picking ratios that aren't polynomials, right? So we can see why we need L'Hopital's rule here. Right? Now, as x goes to infinity, what does the natural log do? If we stop and think graphically, natural log looks something like this. So as x goes to infinity, the natural log goes to infinity. And then what does the root function do? Well, root function looks kind of the same, right? Here's the root function. As x goes to infinity, the root goes to infinity. So we have an indeterminate form of an infinity over an infinity. So I'm going to do L'Hopital's rule here. Again, I'm going to write an equal sign with an LH to communicate to the reader. I'm now applying L'Hopital's rule. So L'Hopital's rule says take the derivative of the numerator. So what's the derivative of 1 over, I just said the answer. What's the derivative of ln of x? 1 over x. And then what's the derivative of square root of x? Again, I'm going to come down here and do a little scribbling, right? Here's square root of x, so I bring the power down, take 1 away. So I really have, 1 over 2 root x if I want to write it that way. I'm going to leave it in this form for a moment. No, actually, I'm going to write it in this form. Okay. All right, now if I go to plug infinity in, check out what happens here. I get, in the numerator, I get 1 over infinity, which is 0. Right? 1 over infinity goes to 0. And in the denominator, I get the same thing. 1 over infinity goes to 0. So I have an indeterminate form, 0 over 0, and I should use L'Hopital's rule again. However, I'm going to put a little note of caution here. When we use L'Hopital's rule the first time, what we always want to do is some algebraic cleanup before we use L'Hopital's rule the second or the third time. So even though I can use L'Hopital's rule again, I'm going to do some algebraic cleanup first. So I'm going to look at this expression here, right? And I'm going to flip and multiply, right? So I have 1 over x times, and then I'm going to flip and multiply 2 root x over 1, right? So I basically have 2x to the 1/2 over x. And when I divide like bases, I subtract exponents. So I'm going to have 1/2, and then this exponent is 1, so I'm going to subtract 1. So I really have 2x to the negative 1/2 when I do the algebraic simplification. 2x to the negative 1/2. And of course, that's 2 over root of x. So before I do L'Hopital's rule a second time, I'm doing some algebra cleanup. And I notice, actually, this is really nice cleanup we end up with. 1 over x over 1 over 2 root x cleans up all the way down to 2 over root x. So this limit, instead of thinking of it as L'Hopital's again, I'm going to do some algebraic cleanup. And now this is what I'm going to take the limit of. Right? So that whole expression is the limit as x goes to infinity of 2 over root x. And again, in a very sloppy manner, the numerator is constant, the denominator, root x, goes to infinity. Right? So that whole limit is going to go to 0 in that case. All right, so what I like to talk to my classes about is using technology to either explore or check our work. Now, we were taking a look at ln x over root x as x goes to infinity, so we could visually check our work. So here's the graph of ln x over root x, and if I zoom out, we can see that that's going to 0 out here, right? It's getting smaller and smaller and smaller and goes to 0. All right, and so, again, I can intuitively see what the limit might be. I could graphically see what the limit might be. I have to justify that work analytically, mathematically, using L'Hopital's rule in this case. All right, I'm having all the fun up here, so I want you to do this one for me. I want you to pause the video. I want you to try this one on your own, and then when you're done, unpause, and we'll talk about this together. All right, now that you have unpaused the video, so first of all, I'm going to plug t equals 0 in and see if we get one of the indeterminate forms. So if I plug 0 in, right, I get e to the 0, which is 1, and 1 minus 1 is 0. And then the sine of 0 is 0. So I do have an indeterminate form here. So I'm going to go ahead then and write an equal sign with an LH, and I'm going to communicate, right, that I'm using L'Hopital's rule. So I'm going to take the derivative of the numerator. Derivative of e to the 2t is 2e to the 2t. The derivative of the 1 is 0. The derivative of sine t is cosine t. So now I'm going to plug 0 back in. I get 2 times e to the 0, which is 2 times 1. And then cosine of 0 is 1. So we see in this example that the limit is 2. All right, I want you again to pause the video. I want you to attempt this problem on your own. When you're done, unpause, and we will talk about this together. Okay, what did you get? Huh? I couldn't hear you. All right, well, let's talk about this together. So you should hopefully have seen something kind of unique here. If I plug pi in, right, what do I get? Let's see, what's cosine of pi? Cosine of pi is -1. And then what's sine of pi? Sine of pi is 0. So I end up getting something that is not an indeterminate form. Notice this is not 0 over 0. This is not infinity over infinity. I do not need to use L'Hopital's rule, and that limit will just be -1. All right, now let's check out this example together. So this example, we have x times ln x as x goes to 0. So, again, let's pretend I can plug 0 in, right? What does y equals x do as x goes to 0? This is just 0, right? And then what does ln do as x goes to 0? Again, here's the ln graph. As we go to 0, ln goes to -infinity. So, what is this limit going to be? Well, be really careful, right? Because 0 times -infinity is not necessarily 0. Again, this would be a, race, which one wins. If this expression gets to 0 much faster, then 0 times whatever would be 0. And then if this expression gets to infinity much quicker, then infinity times whatever would be infinity. So I can't really determine that there is a clear winner here. So we're actually going to have to use L'Hopital's rule. All right, now keep in mind what L'Hopital's rule says is the following. It says that, the limit of f over g will equal the limit of f prime over g prime, right? And that's for infinity over infinity or 0 over 0, right? So the only times we can use it is in that case. Now, what we're noticing in this scenario is we get what we would call an indeterminate product. So we have, in this scenario, an indeterminate product. My pen didn't want to work for a second. So I have an indeterminate product. So the only type of indeterminate product we're ever going to really see here is like a 0 times an infinity. This could be a plus or minus infinity. Right? So whenever we have a 0 times infinity, we don't know which one wins the race, and we have to figure that out. Now, what we're going to have to do in all of these situations is rewrite our product as a quotient. L'Hopital's rule requires a quotient form in order to use it. So I need to rewrite the 0 times infinity, right, as a quotient. So in this example, I need to write x ln x as a quotient. So how do I do that? Well, it's not that difficult in the sense that I'm just going to do like a reverse flip and multiply. So I'm just do a little bit of algebra here real quick, right? How do I write this as a quotient? Well, I could write it as ln of x divided by 1 over x. So kind of like a reverse flip and multiply, right? So if I flip and multiply, if I take the reciprocal of the denominator and multiply to the numerator, I end up with this expression. So I'm just going backwards. And what we end up with in this case is a quotient, and this will be an indeterminate form. So let me come back and squeeze the limits in here. So if we plug 0 in, right, ln of 0 we said is going to -infinity, and then 1 over 0 goes to infinity. So we do get a L'Hopital's form. We get an indeterminate form here. So anytime we have an indeterminate product of 0 times infinity, we're going to do a little bit of algebra to rewrite it in a ratio form. Then we can apply L'Hopital's rule. Now for this example, what's the derivative of the numerator? Well, the derivative of ln x is 1 over x. And then what's the derivative of the denominator? Again, I'm going to come over here and do a little scribbling. 1 over x is x to the -1. So when I take its derivative, it's -x to the -2, which is -1 over x squared. So the derivative here is -1 over x squared. Now, what did we talk about 2 examples ago? We said before we do L'Hopital's rule a second time, if I need to, let's do some algebraic cleanup. So I got a little bit of algebraic cleanup that I can do here. 1 over x times, and let me flip and multiply, -x squared over 1. So just a little bit of algebraic cleanup that we did here. And look how this cleans up, right? One of the x's, reduces down, and I end up with just -x as x goes to 0. So -x, when I plug 0 in, just goes to 0. Running out of digital paper here, I apologize. So in this example, x times ln x as x goes to 0 will actually go to 0. So what that must mean in this case is in this 0 times infinity form, the term that went to 0 must have won the race. 0 got there faster, and in this scenario, 0 times this thing growing without bound actually drove down to 0. Now again, obviously I could do some graphical checking. I could graph x ln of x and see that as we approach 0, we would get 0 out of that graph. Alright, so I'm going to encourage you to pause the video, and I want you to try this one on your own, and then come back and we'll do it together. Alright, how did you do? Alright, I'll tell you, this one is a little tricky. So first of all, let's plug infinity in. Again, wow, that is just, my calculus teacher would slap me on the wrist if I said plug in infinity, because I can never plug infinity in, right? So I'm being really loose here. This is not rigorous. But if I could plug infinity in, right, as x approaches infinity, infinity cubed is infinity, right? And then what's e to the negative infinity? So what I like to think of as here's e to the u, and then as u goes towards negative infinity, the exponential goes to 0. So e to the negative infinity goes to 0, and we get an indeterminate form here. So we need to rewrite this as a ratio, as a quotient. Now, in the prior example, what we did was we took the polynomial term and we did a reverse flip and multiply. I don't want to do that in this situation. So what I want to do in this situation is actually take the exponential and push it into the denominator. Right, so in other words, if I push the exponential into the denominator, it changes the sign of the exponent. So usually, not always, but usually if I have an exponential form with my indeterminate product, I'm going to push the exponential into the denominator. That'll be more productive. Now, if I plug infinity in, let's just point out to ourselves we still have an indeterminate form here. So if I have x approaching infinity, the numerator goes to infinity. And then now we have e to the infinity. Right? So if I go to the infinity in the domain, e goes to infinity. So I have an indeterminate form of infinity over infinity. Uh-oh, I have a little typo here. This should be x cubed here. So I have an indeterminate form of infinity over infinity, and I'm going to do LHospitals Rule. So, what's the derivative of x cubed? That is 3x squared. What's the derivative of e to the x squared? Well, it's e to the x squared times the derivative of x squared, which is 2x. Now again, before I do anything else, I'm going to do some algebraic cleanup. So, a little bit of algebraic cleanup here. The x and the x squared reduced to be just a x in the numerator. Alright, so a little bit of algebraic cleanup. Now we're going to reevaluate the limit. So as x goes to infinity, this linear function goes to infinity. As x goes to infinity, e to the infinity still goes to infinity. So I have LHospitals Rule again. We're going to do LHospitals Rule a second time. So I'm going to say equals LH, and then I have the limit of. So I'm going to take the derivative of the numerator, and that's 3. And then the derivative of the denominator, again, the derivative of e to the x squared is e to the x squared times the derivative of the exponent. So let me just clean this up a little bit. All right, this is 3 over 4x e to the x squared. And the limit is x goes to infinity. So now I see the numerator is going nowhere, right? It's constant. So the limit of a constant is just the constant. And then in the denominator, I get infinity times infinity, right? X goes to infinity, e to the infinity goes to infinity. Infinity times infinity is most definitely infinity, right? And then that's going to go to 0. And there's our limit. So when we have a product, and it's an indeterminate form of a 0 times an infinity, then we need to rewrite that product as a quotient, and then we can apply LHospitals Rule. Alright, now we could also have an indeterminate difference. And the only type of subtraction of two functions we're going to see is an infinity minus an infinity. So if I look at, man, I had to pause the video there. Digital board took a little life of its own. So if I think about this for a second, I have the limit of the difference of two functions, f minus g. As x goes to whatever. I mean, it doesn't matter what x approaches. We've seen that in these prior examples. X could go to 0, x could go to pi, x could go to infinity. So x can go to whatever it wants to. And if I have a difference of infinity minus infinity, that's unknown. I don't know how that behaves. Again, if the first function goes to infinity faster, infinity minus whatever is infinity. Right? If the second function goes to infinity faster, then whatever minus infinity is negative infinity. And then if these go to infinity about the same rate, I'm going to get 0 out of the difference. So this is an indeterminate difference. Now, just like we saw with the indeterminate product, our key here to solving this problem is once we identify that it's an indeterminate difference, we need to rewrite it as a quotient. All right, so let's take a look at an example where we would see an indeterminate difference. So let's say we have the limit as x approaches 1 from the right, and we have, let's say, 1 over ln of x minus 1 over x minus 1. So we have this difference here, and if we plug in x equals 1, what we'll quickly see is we have an indeterminate difference. So if I plug 1 in here, what's ln of 1? That's 0. So I get 1 over something going to 0, and that goes to infinity. And then when I plug 1 into this expression, I get 1 minus 1 is 0. 1 over something going to 0 is infinite. So we have an indeterminate difference of infinity minus infinity. So these problems sometimes need different techniques. How to write this as a quotient. How do I write this as a quotient? So in a scenario where I have like a fraction, two fractions, usually getting common denominators is what will be effective to create one quotient here. So I'm gonna do that. I'm gonna get a common denominator. So the common denominator between these two fractions would be ln of x times x minus 1. That's my common denominator. So on this fraction, I have to multiply top and bottom by x minus 1. And then on this fraction, I have to multiply top and bottom by ln of x. So I just got common denominators here, and I've rewritten as a quotient. Now if we plug 1 in, we'll notice that we'll get a indeterminate quotient here, right? We'll get a 0 over 0 or infinity over infinity. And let's just point out that that's what we get, right? So if I plug 1 in, I get 1 minus 1, which is 0. And we said ln of 1 is 0 as well. So numerator is 0. And then again, if I plug 1 in here, I get 1 minus 1, which is 0. And ln of 1 is 0. So I get 0 times 0 is 0. Now I get an indeterminate form there. Now I have a bad feeling I'm going to run out of digital paper here. So I'm going to do LHospitals Rule. Let me jump down to this line. Let's do LHospitals Rule. All right, so approaching 1 from the right, I'm going to take the derivative of the numerator. So the derivative of x is 1. The derivative of 1 is 0. The derivative of ln of x is 1 over x. And then I'm taking the derivative of the denominator. So I have a product in the denominator. Let's do the product rule. So I have, let's say, derivative of the first times the second plus first times derivative of the second. That's 1 over x. All right, now, a little bit of algebra cleanup here. So first of all, I think what I'm going to do in this case is let's distribute the 1 over x here. So I have 1 minus 1 over x, and then I have ln of x plus, so if I distribute the 1 over x, this becomes 1 minus 1 over x. So here's my expression after a little bit of algebra cleanup. All right, now personally, I don't like compound fractions. I don't like having a fraction within a fraction. So I'm going to do just a little bit more cleanup here. And the way that I'm going to clean this up is I'm going to multiply top and bottom by x. Right? If I multiply top by x and the bottom by x, when I distribute, this fraction goes away. Right? So I'm going to clean up a little bit more. So I have the limit as x approaches 1 from the right. And when I do the multiplication, x times 1 over x is just, negative 1, and then x times 1 is x. And then when I distribute down here, let me jump all the way to the front. X times ln x. And then the x multiplies to the 1, and it multiplies to this fraction. So I get plus x and then minus 1. All right, now I'm happy with that. I don't have a compound fraction. And let's plug 1 in again and see what we get. In the numerator, I get 1 minus 1, which is 0. And then the denominator, I'm going to get, ln of 1 and then times 1. So that's 0 times 1 is 0. And then I get 1 minus 1, which is 0. So I have to do L'Hopital's rule again here. I've done all the cleanup I can. There's no way to avoid L'Hopital's rule here. So let me then LH, apply L'Hopital's rule. So the derivative in the numerator, derivative of x is just 1. And then the derivative in the denominator, I got to do a product rule again. So I have, let's say, derivative of the first times the second plus first times derivative of the second. The derivative of the x here is just 1. And then derivative of the constant is 0. So before I do anything else, let's do a little algebra cleanup. And there's not a whole lot of algebra cleanup to do. X times 1 over x is just 1. So I have the limit of, in the numerator, 1. And in the denominator, I got ln x plus 1. And then plus 1. Ln x plus 2 is what I end up with as x goes to 1 from the right. Now what we excitedly notice here is if I plug 1 back in, I don't have an infinity or a 0 in the numerator. I just have 1 in the numerator. And then when I plug 1 down here, ln of 1 is 0. So this whole thing is 1/2 out of my limit. All right, now there's one last conversation in a section where we discuss L'Hopital's rule. Wait. L'Hopital. Gotta say it like French. Where we discuss L'Hopital's rule, and that's indeterminate powers. So if I have an indeterminate power, what we're really thinking of in this case is like a limit of, an f of x to a g of x. So we have a exponent to an exponent. X could go to whatever. Right? So the different types of powers we're going to have here, we will see like a 0 to the 0 in some situations, an infinity to the 0 in some situations, and then a 1 to infinity. And of course, these infinities could be, plus or minus infinities in those situations, right? And again, I don't want to take the time to explore really deep here, but, 0 to the 0, what's happening here? Well, if the base gets to 0 first, then 0 to any power is 0. If the exponent gets to 0 first, then something to the 0 power is 1. So again, we have a race. Which one of these gets to where it's going first? Again, if I look at the second one, right, if the base gets to infinity first, infinity to some power is infinite. And then if the exponent gets to 0 first, something to the 0 is 1, right? And so on and so forth. Right? So let's take a look at a couple examples here and how we would deal with this situation, because the ultimate key here is I have to rewrite as a quotient to be able to use L'Hopital's rule. Okay, so an example I want to consider here is, let's say we have the limit of x to the power of 1 over x as x goes to infinity. Now again, if I could plug infinity in, I can't really plug infinity in, right? But as x approaches infinity, in the denominator, x goes to infinity. And then in the numerator, we get 1 over infinity, which goes to 0. So we have that indeterminate power, infinity to the 0 power. Now, the difficulty here, and it's really not that difficult, we just need to discuss how to handle this, is how do we write this power to a function to an exponent, right? F of x to a g of x. How do we rewrite that as a quotient form? And this is actually really cool how we're going to do this. So let's walk through the steps. And this is algebraic manipulation, right? So just like with the products, we did some algebra manipulation. Just like with the differences, we did some algebra manipulation. We're just going to do some algebra manipulation here. Now go with me for a moment and we'll see where this takes us, right? Oh, if I take x to the power of 1 over x, I could actually write that as e to the ln of x to the 1 over x. Now, why is that legitimate? Right? So if I switch to red for a moment, we know that e and ln are inverses of each other. Right? We know that those are inverses. Right? E, ln, those are inverses. Right? Log base e and base e exponential are ln. So e to the x, ln of x, these are inverses. So whenever I compose them, they undo each other, right? So if I have ln of e to the x, that's just x. And I have e to the power of ln of x, that's just x, right? So by definition of inverses, when I compose two inverses, they undo each other. So that's what I'm really setting up here. E to the ln of blah is the blah, right? So e to the ln of smiley face is smiley face. So I'm just algebraically manipulating my expression in a very creative way, and watch where this takes us. This is actually pretty cool. Now, remember we have a property of exponents. I'm going to switch to gray. We have a property of logarithms. I apologize. One of the properties of logarithms I call in an algebra class the power rule. So if we have the ln of like a to the b, we can write that as b times ln of a. And in fact, this is true for any logarithm. This could be log base 10, this could be log base 7, whatever this log wants to be. We have a property of logarithms that says when we have an exponent inside our logarithm, we can pull that exponent in front as a coefficient. Now, in an algebra class, we usually go into a deep conversation about why that's true. Remember that logarithm properties are really properties of exponents, just written in a logarithmic form. Remember, that's what logs are. They're inverses of exponentials. Right? So this is basically saying, like, if I have a power raised to a power, I multiply those exponents. All right, anyway, so what I'm going to do in my scenario is I'm going to take my exponent and I'm going to pull it in front as a coefficient. So in my scenario, my exponent is 1 over x. So all of this into the power of e, I'm going to take the 1 over x and pull it in front of the natural log of x. So again, property of exponents, take this exponent, pull it in front as a coefficient, and here's what we have done here. Now, let's come back for a moment to our limit process. So we have x to the 1 over x. We have the limit as x goes to infinity. Come on, digital pen. My pen's running out of ink. X goes to infinity. What is going on here? Sometimes this thing just has a life of its own. Limit as x goes to infinity of x to the 1 over x. This is the limit of our rewrite. E to the power of 1 over x times ln x. Those two things are equal to each other. Right? Now, you may remember a property of limits that says a limit can move inside of a function. So I'm going to switch colors again. Right? That if I have the limit of like, let's say 2 to the f of x, I can write that as 2 to the power of the limit of f of x. So I'm able to move the limit inside of a function. You know, another example of that would be like if I had the limit of square root of sine x. I could move the limit under the root function and then take the limit of just sine x. So I'm going to do the same thing here. I'm going to take this limit, I'm going to literally move it inside the base e exponential. And so what I'm really looking at is e to the power of 1 over x times ln of x as my limit. So now for a moment, I'm only going to focus on the exponent that we have there. What we're really looking at in regards to the limit is 1 over x times ln x. And now that is in a quotient. You notice that? This is a quotient, and it always will be. So I really have ln of x over x as my quotient that I'm looking at. I'm going to pause for a second. So anytime we do this rewrite, let me scroll up. Anytime we do this algebraic rewrite that we did right here, we're going to always end up with a quotient. And the reason why is because when I bring that exponent down in front, I'm always going to have a quotient when I do that. I'm going to be able to manipulate that as a quotient. And this is where we will use the LHospitals Rule. So if we come back to our example here now, let's do LHospitals Rule on this expression here. All right, so I think we might have done this one, or we did something similar. I can't remember. I'm old and forgetful. So as x goes to infinity, the ln goes to infinity, the denominator goes to infinity. So I'm going to do LHospitals Rule. The derivative of ln of x is 1 over x. The derivative of just plain old x is 1. Oh my goodness. I have forgot the limit symbol. Math police are coming for me. So I really just have, when I clean this up algebraically, right, I really just have 1 over x. And 1 over infinity is going to 0. Now remember, let me scroll back up. This was the exponent, right? Right here, this guy, limit of 1 over x times ln x, my exponent. That's the result of that exponent. We get 0. So what we really have is e to the power of 0. So my limit of my original function is really e to the 0, which is 1. Okay. Isn't that cool? That is so cool. All right. So for any of the 3 indeterminate forms, you need to rewrite, and we're going to use that property that logs and exponentials are inverse. So again, whenever I'm doing any of those 3 indeterminate powers, we're going to take f of x raised to the g of x, and we are going to write it as e to the ln of the f to the g. And then I'm going to use the property of logarithms that lets me bring that exponent in front. So I have e to the g times ln of f. All right, so in our example, we actually had a quotient in the exponent, right? But this reminds me, we could actually have a product. But that doesn't really matter, right? If I have an indeterminate product, I write it as a quotient. So the limit of f to the g is just going to be the limit of this expression. And then the limit we push into the exponent. Right? So if I have an indeterminate product here, I deal with it like we discussed before. All right, so in summary, right, in this video we've discussed LHospitals Rule. And LHospitals Rule is one of many applications of derivatives. The way we're using LHospitals Rule in a section like this is we're applying it in manners where we need to evaluate limits. In the past, we've evaluated limits using algebraic trickery, like dividing everything by the largest term in the denominator. But in a section of this nature, I don't always have polynomials over polynomials. And then LHospitals Rule gives us a way to say which one wins the race. All right, hope you guys had a good time. I'll see you in the next video.